Okay, there are no more questions. We can move to the next person. Thank you, Anson.
Thank
So,
you.
Sarah, are you ready for? And you are on mute, so we will hear you right away.
Hello, everyone. My name is Saida, and this is my REU presentation of summer 2021. Today, I'm going to be talking to you about computational fluid dynamics. My mentor throughout this experience is Dr. Kumar, who is a chemical engineer professor at LSU. So my project is a combination of computer science and chemical engineering. And for those of you that might not be as familiar with the term, chemical engineers are the ones that apply the principles of chemistry, biology, physics, and math to solve problems that involve the use of fuel, drugs, food, and many other products. So the goal of this project is to innovate the field of chemical engineering using the help of computation. If we could then computationally modularize aspects of this field, we will then be able to save time, money, and reduce pollution. My contribution to innovate the chemical engineering field is shown throughout my work this summer, as the work I have done this summer helps in developing better closure models for drag forces versus relative velocity. And this type of studies help in improving the forces versus velocity relationship in fluidized beds, for example. But in fluidized beds, there are billions of particles, and unfortunately, this level of detailed simulation is not possible as of today. So we do something called averaging of equations instead. And this is exactly where the periodic ellipse problem comes into play. So for this problem, this was given to me by my wonderful mentor. I have three different geometric figures. Each figure has a different number of particles. Each particle is set in a specific location, but they're free to rotate. And my goal for this was to change the kinematic viscosity so that I could simulate different Reynolds numbers. I was able to put together 27 cases throughout the summer, but out of the 27, I'll be showing with you guys 6 of those. So over here we have case 1. This red over here represents the particle and the blue represents the fluid. And as you guys can remember from the previous slide, the Reynolds number is just h times u over v, where h is the height between the plates, u is the plate velocity, and v is the kinematic viscosity. So to understand what Reynolds number even is, let's take, for example, honey and oil. Honey and oil have a very high kinematic viscosity number, which translates into a low Reynolds number, where water has a very low kinematic viscosity value, which translates into a high Reynolds number. When taking a look to the figures over here, these are the graphs that I obtained from the simulation. They're the time series of this simulation. The very first one represents the angle of inclination of the ellipse. The second one represents the angular velocity. And the last one represents the torque on the particle causing the rotation. And all these graphs show a very regularly periodic response to the uniform force and velocity of u equals 1. I do want you guys to notice that these particles are perfectly in sync throughout the entire process. So upon increasing the Reynolds number to 100, still focusing on the two ellipses interaction, we see a relaxation response. So for instance, when the ellipses are oriented horizontally, the angular velocity is very small, and it takes a long time for it to move. But once it starts moving, it reaches the vertical position very quickly and returns to the horizontal position. And once again, here our ellipses are in perfect sync, but we see that relaxation behavior. Moving on to the next case, here we have 4 particles and the Reynolds number is equals to 5. I do want you guys to notice that the particle on the upper left and the particle on the bottom right are perfectly in sync, whereas these 2 particles are in sync as well. And we're gonna move on to the next simulation. And once again, we're gonna see the same behavior and synchronization as to particles wise, but we do reach that relaxation behavior one more time. And what's interesting about this one specifically is that when we take a look at the angular velocity graphs, we see a phase difference. So these are laid out just the way that the simulation were laid out. So here we have particle 0, particle 1, 2, and 3. And as I mentioned to you guys before, particle 0 and particle 3 were perfectly in sync. And as you guys can tell, these graphs are identical. And I also told you that particle 1 and particle 2 were in sync. And as you guys can see, these graphs are also perfectly identical. Moving on to the very last case, here Reynolds number is equals to 5. I have 6 particles. I was not able to find a pattern in between them, but this was integrated from 0 seconds to 400 seconds. So maybe the student that comes after me next summer will be able to integrate it for longer and see if they can find a pattern. However, if there is not a pattern, it doesn't really mean much. It just means that this is actually better for mixing the previous simulations we had before. So it's not like a bad thing. Some of you might be wondering, like, why are the particles moving? Well, the forces acting on the particles are unbalanced. And if the net force is not 0, the particle will move. You guys might also be wondering, what are the forces that are acting upon these particles? And well, we have the shear force by the fluid on the particle surface, we have gravity, and we have buoyancy on the entire volume. Moving on to the same case, but when the Reynolds number is equal to 100. Once again, I did not find a pattern between this, but we do see that relaxation behavior that seems to be very like a pattern. Whenever we increase the Reynolds number, we seem to be finding the relaxation behavior. And so something very important that we found throughout these experiments was the more particles you introduce into the mesh, the more chaotic behavior we seem to be finding, while when we have fewer particles, they seem to be reaching synchronization very quickly. So throughout this experience, I was able to learn a whole lot of things. Some of those things were OpenFOAM and ParaView, which are open source software. With OpenFOAM, I put together my meshes, I put where the particles were going to go, I gave them the motion they were going to have. With ParaView, I was able to visualize everything. And I was also able to put together those simulations that you guys saw. But overall, my biggest takeaway was chemical engineering. I had no idea what chemical engineering was before coming into this, and I feel like I learned a great deal. And for that, I would like to thank my mentor. So thank you. With that, are there any questions?
I have a quick question. You mentioned you didn't really find clear pattern, but did you find any subtle, any pattern, the particle simulation?
Yeah, so for the first case where I had the 2 particles, I saw a clear pattern there. For the one that I had the 4 particles, I also saw a clear pattern. So there seemed to be that on the first case, the 2 particles were perfectly synchronized. And in the second case, I was able to see that 2 particles were synchronized where other 2 particles were synchronized. But with the very last case, there was not such synchronization between the particles whatsoever. So it was a very chaotic behavior.
Thank you.
Yeah.
Any other question or comment?
Just a comment. You did a fantastic job. I'm really impressed with what you did.
Thank you, Dr. Kumar.
Yeah, I have just a question. I'm curious. I mean, the problem you are solving is symmetric, no, with respect to the line in the middle.
Correct.
No,
Yeah.
So,
Yeah.
so that symmetry should be reflected in the behavior of the particles, and you find it for a small when you have 2 or 4. So, as you say, if you run it for longer, will you find that behavior? I mean, it's a numerical method or not?
Sarah, do you want to answer that? That's a very difficult and a very profound question. And I think the answer to that lies in stabilities of these flows. So you may have a symmetric solution, but if it is unstable, then it goes into symmetry breaking bifurcation, and you will have multiple solutions, etc. And so there's a highly nonlinear behavior that we are fundamentally interested in. The reason I jumped in is we haven't discussed this specific answer, but that's one of the driving forces for us to look at when these symmetries are broken, how they are broken, and because when you have millions of particles, there is no symmetry, right? So what can we learn in the symmetry breaking process to learn about cluster formation? Why do the particles form clumps in fluidized bed in real life? So it's inspired by that. I didn't mean to inject, Sarah. If you have a comment to make, please go ahead.
No, it's okay. Thank you, Dr. Kumar. I appreciate that.
Taron?